Alright folks, welcome back to our module on the one-way ANOVA, the first of our family of ANOVA tests that we'll be talking about, but don't panic. The other ones we don't actually do much in terms of running, we mostly talk about them conceptually. In the first few videos we set up some of the basics of the ANOVA test, and in this video we are going to be putting it all together in order to talk about the actual 5-step model by which we test hypotheses in ANOVA. In the next video we will be doing some example problems, and we'll continue on from there to some additional concepts. So this is a big pivot here, but again, remember that in our hypothesis tests our 5 steps don't change. The first step here is we're still providing those null and alternative hypotheses. Between the two of them, they account for every single way that the parameters we're interested in could relate, and in this case the parameters are all population means. The big change in the ANOVA, of course, is that we now are talking about at least 3 different population means. In every earlier test it had been 2. So because of that and the added complexity of adding a third or more population mean, we are going to be changing our hypotheses. We're not going to express them symbolically. So the null hypothesis is still the hypothesis of equality, but it's just a generic statement that all the populations we're comparing, they all have the same mean. If we have an IV, it means the IV is not doing anything. If we have a quasi-IV, it means the groups don't differ. It's just nothing going on. So in an ANOVA, we can express this symbolically like this. mu1 equals mu2 we've seen before, but now we've got mu3, and what's that k mean? K basically means as many as you've got. The ANOVA can work for 3 populations, it can work for 10, it could work for 100, though you wouldn't want to do that. So k just means however many means you have, they're all equal. The alternative hypothesis is again the hypothesis of difference, but here that becomes a little less nuanced, a little more generic. We are saying at least one population mean is different from the rest. We can't express this symbolically because there's lots of different ways that this statement here, that these 3 mu's all being equal, there's lots of different ways that that could be untrue. mu1 could be different from the rest, mu3 could be different from the rest, they all could be different from each other. And if you have 4 or more population means, it gets even more complicated. So instead of trying to write out every single possibility, what you want to do is just say generically at least one of them is different from the rest. These are all non-directional two-tailed tests. That's the way we'll be running it from here on out, although it makes actually very little difference in terms of what you do with the comparison distribution. So remember, at the end of this test, we're going to be calculating this F ratio that's going to test our null hypothesis. And recall the different sources of variance. Our treatment effect is only in the numerator, but our individual differences in error are both in the numerator and denominator. So if the null is true, if everything is equal, we expect F to be around 1. Reason why, if there's no treatment, you have the same factors in the numerator and the denominator. You'd expect them to be about the same. When the null is false, you expect F to be bigger than 1. And the more influential the treatment gets, the bigger and bigger that ratio will get. So just a little bit of a sneak peek ahead of how we'll be testing this hypothesis. But in terms of the test itself, still just name your null, name your alternative. Not a lot going on here. We're just adjusting for having 3 or more mu's of interest. Step 2, we define the characteristics of our comparison distribution. This used to be one of the very longest steps, and now it's actually one of the shortest. All we actually have to do at this point is just assess the shape of the comparison distribution. So we don't know any parameters. We have a between participants design, more than 3 samples, and 1 IV or quasi-IV. We've talked about that already. That's why it's called a one-way ANOVA, the one factor. So we'll be doing an F test here. All we have to do is define what that comparison distribution looks like, and that just means providing the shape. To do this, you have to say that it's an F distribution, but you also have to calculate 2 different degrees of freedom. You have to calculate a between groups degrees of freedom, sometimes called the numerator degrees of freedom. That's just the number of groups you have minus 1. You have to calculate a within groups degrees of freedom, sometimes called denominator degrees of freedom. That involves calculating degrees of freedom for each group separately, just the number of people in the first group minus 1, number of people in the second group minus 1, and then adding them all up together. You also can get degrees of freedom within by just subtracting the number of groups from the number of participants if you want. The nice thing about this is you can also reverse the process. If you know degrees of freedom between, you know how many groups you have, you just add 1 to it. If you know degrees of freedom within, you know how many people were in the study, you just add the number of groups to that total. So that's step 2, that's all we have to do. You just have to remember how to calculate those degrees of freedom. Step 3, we're going to get our critical value, the value that's going to determine whether we'll reject the null or not. Alpha is still 0.05, still 0.01, still not anything you'll have to determine. It'll be provided for you. You can find your critical F score by using the table B4, which is a distribution of F values. Again, that's going to be available in this modules folder. And as always, you might use it some for your practice problems, your homework problems, but you won't be using it on anything graded. It's not a skill that we really want to test. It just illustrates kind of how this works. So notice again that we only have F values for 0.05 and 0.01, and what color the text is determines that. Also notice that you need degrees of freedom separately for the numerator and the denominator. That's your between groups or treatment degrees of freedom. The denominator is your within groups or error degrees of freedom. This is always written with the degrees of freedom between first and the degrees of freedom within second. So you could look it up and say, okay, if I have an alpha of 0.05, I have 2 degrees of freedom between groups, 15 within, what would my critical value be? Go ahead and you look it up and you find, okay, 3.68. This means that F ratios greater than 3.68 have less than a 5% chance of happening in that particular distribution with those degrees of freedom. By the way, note that I can reverse this. How many groups were there in this study? I can add 1 to this first number and say, okay, there are 3 groups. How many participants were there in this study? Okay, if there's 3 groups and there's 15 degrees of freedom within, you can add them together. There are 18 people in that study overall. Don't know how many were in each group, but I know there's 18 overall. Same thing here. Here we have slightly different degrees of freedom, different alpha level. We can look that up and find, okay, now we need an F ratio of 4.94 or higher to be in that region of rejection. A little harder to do in that case. Again, we can look at these degrees of freedom and find there are 4 groups, 3 plus 1. We can add that to our degrees of freedom within and say, hey, we have 24 people in the entire study. But that's step 3, and again, on something graded, you're just going to be copying down a number that I'm going to give you. Step 4 is the one that will take you more time than all the other steps put together. This is the long one. It's the one where you will calculate your between and within groups variance and turn them into an F ratio. Here's something that I strongly recommend, but I'm not actually going to be assessing you on. As we get into more complicated data sets, it gets easier to get disorganized, to mix up different figures, to make really simple mathematical errors that will cost you some points, or to report things incorrectly. I highly recommend at the beginning of step 4 that you build what's called an ANOVA table, and there's an example behind me. This helps you organize your information and your calculations and helps you figure out, again, what your F ratio is. Again, it makes it a lot easier to get to that point because there's a lot of intermediate calculations. So again, here's what it looks like. We have between and within as our rows. They're sometimes called treatment and error. We have another row for the total. Sometimes some people will put the critical value from step 3 down here with your degrees of freedom. But notice our columns here. This first column, you've seen that figure before. That's a sum of squares. Sum of squares, again, has come roaring back. We're going to be calculating multiple sums of squares. You have your degrees of freedom, which you already would have gotten in step 2. You have it for the first 2 rows. How do you get the total? Just add those 2 numbers up. By the way, degrees of freedom total should be the total number of people in the entire study minus 1. Good way of checking that. Here we have a column called mean square. Mean square we haven't seen before, but mean square is basically what we use for our variance. It's how we calculate our variance. It's just referred to as a mean square in this framework. And then over here we have the actual F ratio we're ultimately looking to get to. So let's break down how we're going to get these pieces of information. First, when you start, you should already have degrees of freedom between and within, and you should be able to add them up to get degrees of freedom total. That's just something you'd have in step 2. But the rest of it we're going to have to figure out. So we start by calculating sums of squares. Again, the sum of square was the numerator to our variance formulas. We've been working with sum of squares all the way since back in module 4, but we are really going to need to be good at those formulas and efficient with those formulas now. So the first thing we're going to do is find the total variability, which is represented by this total sum of squares. Notice that subscripts start to become really important now too. So that's the figure that would eventually go right here. That's your sum of squares total. Notice that you should already have all of your degrees of freedom taken care of. So here's our formula. And you've seen this before, this is the numerator to your variance formula. It just has subscripts of tote to represent that it's every single score in the entire data set. So it doesn't matter what condition the scores are in, where they're organized, just every single score gets thrown in together. We add them all up, we square that result, we divide it by the total number of people. Over here, because again there's no parentheses, we square each score first, then add them all up together, and we subtract, and we get the sum of squares total. So it's a formula you've seen before. The thing to remember is just that every score in the data set is thrown into this formula. Now we have a measure of our total variability. We're going to split that up between the between groups and the within groups, sometimes called error variability. We're going to calculate sums of squares for each. So first we calculate what's technically called the sum of squares of the error, but that corresponds to our within. Again, that'd go in this little box here. And all that we're doing here is using that same sum of squares formula, but doing it separately for each condition. So just for the people in group 1, just for the people in group 2, just for the people in group 3, so on and so forth, and then we add them up. You're basically using this formula. Here's the computational formula I recommend, but here's that definitional formula if you want to use it. You're basically using this formula once for each group, just for the scores in that group, and then adding them all up together, and that will get you your sum of squares within. Here's the good news. The sum of squares of the treatment are between group sum of squares, which is going to go up here. We can get it very easily. Because sum of squares total is only made up of within and between sum of squares, you can figure out sum of squares between by just subtracting within from total. So fortunately, it's pretty quick at this point. Just whatever's left over when you subtract within from total. There are other formulas that you can get sum of squares between directly with. We will talk about those a little later on when they're meaningful, but see the book if you're interested. So I highly recommend before you move on that you stop to check yourself, because here's the thing. If your sums of squares are calculated incorrectly, you may get multiple ones wrong, especially if your total is wrong, then you are going to have the wrong between as well when you subtract. So you can have multiple mistakes in this step, and they can be kind of interrelated. But the sum of squares is going to be used in your mean squares over here. So if your sums of squares are wrong, your mean squares are also going to be wrong. And if your mean squares are wrong, your F ratio is going to be wrong. And if your F ratio is wrong, you might make the wrong decision about the test. So a lot of things can go wrong if you don't get the sums of squares correct. Always stop to double check. First, they have to always be positive numbers. They can only be 0 if every single score is identical. They can never be tied. Next, make sure that your sums of squares add up to that sum of squares total. But once you've done that, you're checked any work that you've done, we can turn those into mean squares. You can think of a mean square as basically a variance. Here's our formula for mean square between. Again, we have subscripts here, but it's just sum of squares divided by degrees of freedom. Hey, that's the same thing as that variance formula. Why do we call it mean square here and not elsewhere? I don't know. It has something to do with the people that originated ANOVA and how they preferred to describe these things. But it basically is a variance just with a different label. For error or within groups variance, same equation, just plug in sum of squares within and degrees of freedom within. Hey, look at this table. All that we're doing is dividing across. There's our numerator, there's our denominator for between, and we plug the result in there. Same thing for this row, divide across, plug it in there. Now we already have the numerator and denominator of our F ratio lined right up with each other. So mean square with between and within. So in addition to just organizing the results, it also aligns them in a way where the calculations are more intuitive and easier to remember. So that's our F ratio, and that's what we really want to know. That's our test statistic. Again, it's the variance between groups divided by the variance within groups, which represents the expected sampling error. It's our basis of comparison. So we can check everything in our ANOVA table here, and if we have the critical value at the bottom, you can easily compare your number here, your test statistic, to your critical value. If it's higher than that critical value or tied, you reject the null. If it's not, you don't. So just make the comparison. If it's beyond the threshold, the critical value, reject the null. If it's not, retain or fail to reject it. All right, next up, we are going to walk through an example of this with actual data. Again, really important stuff. Very likely you'll be tested on this. So I will see you in that video.